Okay, we're going to get started. Good afternoon, everyone. Welcome. Thank you for coming to this panel. I'm really delighted to moderate this panel, Preparing for the Future, Innovative AI, Machine Learning, and State-of-the-Art Modeling. State-of-the-art modeling tools to collect and analyze data for oceans and climate. I'll begin with some of my own perspectives and those of NOAA on AI for Earth observations, predictions, and services. AI and machine learning are bringing transformative changes to Earth observation, prediction, and related services through maximizing the utility of observations, speeding up analysis times, and accelerating the execution of predictive models to allow for timely and accurate guidance to decision makers. Additionally, AI is allowing for the provision of forecast information to forecast consumers in their native languages and helping programmers with accelerating code development. I note that earlier this week, on Earth Information Day, Dr. Rob Redmond, director of NOAA's Center for Artificial Intelligence, gave an exceptional talk on NOAA's AI work. And you can find more about what NOAA is doing with respect to AI if you go to noaa.gov/AI. So AI and machine learning enables us to analyze and interpret vast data sets from Earth observation sources like satellite imagery, sensor networks, subsurface ocean cameras and microphones, and uncrewed observing systems at greater scales and speed. This capability allows for more accurate insights into the current environment, as well as environmental changes and trends over time. Earth observation data is voluminous, and well-trained AI algorithms excel at sifting through this information to detect subtle patterns that would otherwise possibly remain hidden to humans. With AI-powered analyses, we can monitor environmental indicators like vegetative cover, water levels, and pollution in real time, providing critical data for conservation efforts and disaster response. Machine learning algorithms help track climate indicators and environmental risk, contributing significantly to sustainability efforts and proactive disaster management. These AI models, particularly those with deep learning techniques, may enhance the precision of climate predictions and weather forecasts by capturing complex nonlinear relationships within the climate system. Traditional climate models have limitations in resolution. AI can complement them, leading hopefully to more accurate long-term climate projections. Through predictive modeling and real-time data analysis, AI allows for the early warnings of natural disasters such as floods, hurricanes, wildfires, helping governments and communities prepare more effectively. AI's predictive power in disaster risk management can save lives, reduce economic loss, and improve emergency response times. With respect to early warnings, the incredibly large amount of information and knowledge products available makes it difficult for any organization or institution to be able to be fully aware of or utilize that information in the decision of early warnings, or to most effectively make decisions on what to do with early warning information. AI and advanced data management systems can multiply the effectiveness of early warning systems, as well as support early recognition of the need for a warning, fully understanding potential impacts, and determining how to react and address consequences. The sharing of research and approaches in this area will help all countries and institutions engaged in providing or using early warning systems. AI also plays a role in digital twinning. NOAA, the National Oceanic and Atmospheric Administration, is starting to pursue innovation in digital twins for the Earth system to solve challenges around Earth system predictability, diverse data integration and modeling, uncertainty quantification, and communication. The ultimate goal, with appropriate resources, is to advance our Earth system modeling capabilities at local community scales. This initial effort will include integrating weather, climate, infrastructure, and socioeconomics to support community-level pre-event resilience planning, quicker and more accurate emergency management, and post-event mitigation. As an example of our international partnerships in this space, we are partnering with the EU on AI for public good on extreme weather to develop 2 use cases covering tropical cyclones and urban heat stress. Allow me to say just a little bit more about these AI-driven predictive models, or emulators. With the recent emergence of these models, the enterprise of weather prediction is undergoing a transformation unrivaled since the advent of physics-based numerical weather prediction models in the middle and latter half of the last century. AI will drive our predictive models and allow for the creation of bespoke forecasts. These data-driven models, initially developed within the private sector, have shown predictive capabilities that match or exceed, in many respects, those of our traditional physics-based models. They're fast with the execution time, in fact, several times faster than conventional physics-based models. The skillfulness and rapid execution time of these models opens the door for more timely forecast, lower computational costs to run, enhanced use of available observations to improve situational awareness, and reduction in forecast uncertainty. as well as generating ensembles capable of more accurately quantifying forecast uncertainties. Even with these expected benefits, hurdles in achieving the promise of these models include data limitations, a lack of trust and understanding of the algorithms themselves, making forecasters hesitant to perhaps use these in operations. The training of the models is, in fact, computationally expensive, and the need for greater domain expertise involved in the model development. The societal risk in the implementation of these models exists. The possibility of missing high-impact extreme weather events. The post-processing of model output to provide bespoke forecasts requires knowledge of the forecast consumer. This raises privacy and security concerns that must also be addressed. To realize the operationalization of these predictive tools, we must clear these hurdles and mitigate the societal risk. To do so requires investments in data sharing infrastructure, compute, human capital, and building trust. Moreover, it requires partnerships across federal, academic, nonprofit, and private sectors. These partnerships require building an open science infrastructure to support community data-driven model development. Trust earned by putting these models through the test at NOAA's operational environments, like our forecast test beds, hazardous weather test beds, and within our weather forecast offices. And these models would undergo this sort of spiral development process where which feedback from forecasters and test beds is incorporated into model developments and then retested in operations. AI weather forecast emulators are going to contribute to improving the accuracy and timeliness of weather predictions. The benefits span across a variety of sectors, enhancing public safety, optimizing business operations, and contributing to more effective disaster management and environmental protection. The integration of AI in weather forecasting thus holds the potential to transform how both the public and private sectors respond to and manage weather-related challenges. While AI brings these powerful capabilities, we must address issues of bias and data quality to ensure that the models are in fact reliable and provide representative insights across diverse geographic and socioeconomic contexts. Data gaps and biases and the need for high-quality labeled data sets are also a significant challenge in AI-based Earth observation, as these can lead to inaccuracies. And finally, challenges include the need for a skilled workforce, reliable HPC for training data set generation, and GPUs for training and easily accessible training data sets themselves. So at this panel discussion that we're about to have, we're going to be discussing these issues and many more related to climate, and I'm really delighted to introduce our panelists. Dr. Venkatachalam Ramaswamy, Director of NOAA's Geophysical Fluid Dynamics Laboratory. Ram is the director of NOAA's GFD lab, focusing on understanding and predicting the Earth system through advanced numerical models. His work spans applications like weather forecasting, climate modeling, and addressing environmental extremes such as hurricanes and sea level rise and wildfires. Also, we have Mr. Ray Gopher, co-founder and the chief strategy officer of Tomorrow.io. His portfolio of activities includes Tomorrow.space and the company's government business unit. Ray also serves on the board of TomorrowNow.org, the nonprofit partner of Tomorrow.io, focusing on climate security for underserved communities. We also have another panelist that hopefully will be able to arrive and get through security with some badge issues, Ms. Justina Nixon-Santil, and she's the vice president. She's IBM's vice president of corporate social responsibility, chief impact officer, leading to initiatives to empower communities through skilled volunteerism, education programs, and sustainability efforts. Again, she's not here at the moment, but we hope that she'll be joining us. But I'd like to invite Dr. Ramaswamy and as well as Mr. Ray Gopher to come up to the stage, please. And we're going to begin with Dr. Ramaswamy presentation to begin to have some opening remarks before we get into the panel. So Dr. Ramaswamy.
Okay, good afternoon, everyone. I think there are three things that I want to touch upon: AI, the digital twins, and high-resolution modeling, which kind of goes along with these two other things that Dr. Morgan talked about. Next slide, please. Oops. Okay, so what we are trying to now capture is the Earth system, which consists of the atmosphere, the oceans, the cryosphere, biosphere, and ecosystems. Now, the tone of this session is on oceans, so let me just say this outright. Oceans determine climate. Okay, let's maybe start from that premise and move on from there. And what you see are on the left, the simulation with the high resolution model of the atmosphere going at 3 kilometers. And then the ocean is at 25 kilometers. You see it moving slowly because of the currents. Next slide, please. So I want to touch upon two items, which is NOAA-wide, and that is the use of AI increasingly in several respects. One is just providing more accurate weather forecasts. This is something that's really now been galvanized by a whole host of institutions, and certainly is promising very improved forecasts at a faster rate than before. Then you have, on the ocean side, the uncrewed systems for bathymetric mapping and geographic surveys, where also AI is being used by NOAA. And then the protection of the species is also being, also seeing involvement of AI in terms of images and acoustic recordings. And then you have the space weather issues, and AI is also being used there. So these are some of the applications that you're seeing of AI in NOAA's vast array of things involving artificial intelligence needed and speeding up things in terms of deliverables. Next slide, please. So this is now getting to where AI is now getting increasingly used in not just observations and monitoring, but also in prediction and assessment. So the monitoring is what you're seeing is an AI-based data assimilation. So data assimilation for models and for prediction is making tremendous strides with the use of AI. It's flexible, cost-efficient, and agile. Those are sort of three very important characteristics that go along with improving the tool for monitoring. And then in the prediction, the digital twin, which is in a sort of a basic essence, it is the development of numerical tools which simulate the planet. You can't have another planet do experiments, so this is a planet that you do get to use using numerical tools. And that is, again, now you'll see the sort of subsequent slides how improved resolution, increased resolution is actually playing a big role in more modern day predictions. And then the assessments involving a whole host of things ranging from weather to climate timescales, all sorts of phenomena, trends, and including extremes. AI, again, is being used increasingly in all these things. I won't have time to go through all the examples, but I will give you an example at the end of how it's being used. Next slide, please. So this is an example of a 3 kilometer atmosphere model. 3 kilometers is really, really very fine. And the sort of elegance of this is that you're seeing the winds being captured in a very fine, detailed manner. And you can even see vortices forming, which again are the precursors to hurricanes and storms because of the rotation. And this is now giving really a great opening into how we can resolve very severe weather and therefore get to the simulation extremes. And this model is being used now widely, not just in NOAA, but also by NSF and also NASA. So this is actually something which is being very widespread use. Next slide, please. And now we go to the oceans. Another click. Another click, yeah. Okay, so on the left you see the global ocean model at 1/8 of a degree, 20 kilometers. This is a resolution which is actually starting to hit at the mesoscale eddies. Now the mesoscale eddies are an important component of the ocean because they actually determine a lot of things about both the heat transport from the low latitudes to high latitudes and also the formation of weather. This is kind of why I said at the preface that oceans determine climate and weather. And then on the right panel, you actually see what's called the regional version of the global model, which gets down to 5 kilometers along the coastlines. Now, this is becoming very useful because it actually offers the connection of the global ocean model to a regional ocean model using exactly the same physics. It's just a higher resolution. And now, of course, the regional model, because of computational limitations, you've got to devise it for particular coastlines. What you see is the East Coast, and you got to see in very vivid and sharp contrast the Gulf Stream, actually transporting the heat as well as forming the eddies. And if you look at the bottom right panel, you see climate ecosystem fisheries. This is a new initiative in NOAA where these kind of models are being used not just for getting the physical aspects of the coastlines and the coastal systems, but also the ecosystems along the coast, also the ocean, also the coastal physics, like the involvement of tides, the basins. All those things are very important because human beings live along the coastlines, and so that simulation of that is very important, and that is affecting marine ecosystem determinations. And NOAA has a mandate in the U.S. for marine ecosystem observations and preservation. And then, of course, the all-important thing is the sea level rise estimate. These fine models along the coastlines are actually helping also to determine estimates of regional sea level rise, which becomes very important because the global sea level rise is one thing, which is being determined by the warming of the oceans in general, but then regionally, you have lots of other physical factors which are then captured using high-resolution models. Next slide, please. Oh, before I leave the slide, I would also mention that in the importance of mesoscale eddies, actually now is being computed using AI parameterizations, because the AI helps you to get to a speedier model, more efficient model, but you still have to get the mesoscale eddies right, which are very fine grid scale phenomena. So the AI actually is helping you to combine these things between the very fine scale modeling, very fine scale regional modeling, as well as the global scale modeling. Now, this is an expansion of the regional model along three different, along sort of this is actually for the west coast of the US and also the Arctic. And what you can see now is the regional models not only contain the physics and dynamics, but also the biogeochemistry. So you're able to actually capture the biogeochemistry happening along the coastlines, and not just things happening in the ocean. You have nutrients coming along the rivers into the oceans, and trying to get the biogeochemistry of that as they come into the coastal regions, giving rise to hypoxia and other things. This is the kind of thing now that high-resolution modeling combined with AI is helping you to determine and visualize. Next slide, please. So this is like a generic slide where we're talking about the weather and climate extremes that NOAA is focused on, and you can see really all the extremes that you can think of, which are perturbing the human society: wildfires, droughts, floods, heat, coast, and then the preservation of marine resources, as well as ideas of how mitigative strategies can be adopted. Again, on the basis of these models, using high resolution, using AI, and then giving way to giving you the inputs into management decisions in various sectors. And then the last slide is an example of how high resolution and AI has been used for predictions. Normally, we kind of develop models to do process studies and projections. This is an example of actually the same model used for climate projections being used for predictions, where this is actually the spatial patterns depicting the three predictable components of the frequency of hot days, so hot summer days, over North America. So this is an example of application to extremes. And you see that there are three predictable components which are distinctly identifiable using these models, high-resolution models. So one component is just external climate forcings, greenhouse gas increases, land use changes, and aerosols. And you can see that gives you a heat wave propensity over the entire US. But then there's another component which is determined by just the selective changes in the North Atlantic, North Pacific Oceans, combined with contribution of US soil, land soil moisture. And that gives us a component where the warming is exacerbated around the southeast US. And then there's a very familiar dipole pattern due to the Central Pacific El Nino occurrences, where you see there's selective warming in the southeast, but a relative cooling or less warming in the northwest. And these three components are predictable using these high-resolution models. And therefore, this gives us really the hope that you can actually capture extremes built upon whatever is happening in the background of climate change. So that's kind of all I have, and I'm happy to take questions.
One quick question for you, Ram, before we go to our next panelist, and then we'll open it up for everyone. How do climate models generated by an agency like NOAA benefit the end users? And how are emerging technologies like AI/ML resulting in improved products and services for communities in the US and abroad?
So I think so. Let me answer this in by harking on 2 points. One is these models are actually paving the way for determining the extremes in weather atop climate variability and change. So climate varies, El Nino, La Nina as classic examples, the interdecadal oscillations, another example, and then of course there's externally forced climate change. Now, riding on this are the extremes in the weather, and I might say that they're mostly determined by happenings in the ocean, especially subsurface ocean, and that circulation is actually triggers, for example, medium range and subseasonal to seasonal patterns. So that's one way in which these models are actually now helping to do the prediction aspect. So it's like a seamless thing. Weather to climate is seamless, and what you're now trying to do is a bridging of the weather and climate, where the weather is kind of riding atop the climate change. Another example is sea level rise. I mean, there is sea level rise going on, but then there's weather that gets shaped up by the ocean circulation, and that too is something that these models are getting to be used for. The second aspect I would say is that as we are building more and more complex models, where increasingly, I mentioned at the outset, atmosphere, ocean, cryosphere, biosphere, ecosystems, the knowledge is advancing in each aspect. And so when we think of the Earth system now, this actually has to fold in all these aspects. One thing that happens is how the extremes in one variable get cascaded into other variables. So it's actually what you see when extremes happen is multiple extremes happening because of some primary, let's say weather pattern shifting. And that is very important because now then you're cascading down to not just temperature and precipitation changes or sea level rise, but also how it's maybe affecting terrestrial and marine ecosystems. And that ultimately then links up to perturbations that relate to societal impacts. So I've mentioned those two examples those two kinds of examples as something where these models are definitely improving the category of products and services to stakeholders.
Okay, thank you very much. Next, we'll have Ray Gopher giving a brief presentation.
All right, so great to be here. Thank you for having me. And better now? Right. All right. I'm super tall, so. All right, so for those who don't know Tomorrow.io, we are a Boston-based weather intelligence company. Startup, VC-backed, about 150 employees, 8 years in business. So what we do is provide a weather intelligence platform, which is a software that helps both businesses and government agencies to handle their operations with regards to the weather. We start with that, but we actually go quite deep behind the scenes, both developing AI models and developing and launching our own weather satellites to increase global coverage and observations. And so I'd like to start with that. We just heard about weather models and ocean models and how AI can improve them. But I think you've all heard the term garbage in, garbage out, which refers to the fact that even the best AI models, the best, magics, definitely physics models, are limited by what we feed them with. And what we feed those models with are observations of the current state of the atmosphere and the oceans. It's a bit of an unknown secret, but in over 80 years or so of development of these models and the forecasting systems, we've still managed to cover but a small fraction of the globe with most of our sensing instruments. So this picture here comes from the WMO, the World Meteorological Organization, and they carry a database of every type of observing system, from radars to buoys to surface observations, and show them on a map. So this particular map is of radars, ground-based weather radars, which is one of the most important tools we have for many, many modeling applications, short-term, nowcasting, flooding, to name a few, but they also obviously help us inform our larger scale and longer-term models. So radars have been around since the 1940s, actually Second World War, invented by the US Navy. And 80 years later, we've only managed to deploy about 1,000 of them globally. Vast majority of them cover about 5% of the globe: US, Europe, Japan, coastal Australia, and a handful of other regions. all of Africa, most of Latin America, most of India, most of Asia, zero coverage. And you might also notice no coverage over the oceans. Now you might ask yourself, why do we care about precipitation over the oceans? Well, we do because all the severe weather events from tropical cyclones to atmospheric rivers actually generate in the oceans and hit land towards the end of their life, not when they begin. So this map actually shows us one example of big gaps. If I showed you a map of surface observations, buoys, radio sounds, any type of other instrument, it would look the same. And despite what we might hope and believe, no AI magic is going to solve that gap. Like we don't have a solution around the initial conditions. And of course, there is also a really interesting opposite correlation between that map and sensitivity to climate, right? We're here in this COP week talking about all the communities that are most impacted by climate. Actually, those communities live in areas where there is the least amount of instrumentation, least capable weather infrastructure to give them the insights they need in order to better deal with these changing weather patterns. So this is kind of this huge market failure or huge failure of the entire ecosystem of weather enterprise globally, which really has not been able to provide a valuable solution for the vast majority of people. We're talking about 5 billion people around the globe that live outside of reliable coverage. So we at Tomorrow took on ourselves a bit of a small task, trying to solve that gap, or at least make a meaningful dent in it. Very proud to be named one of Time's most 100 influential companies, and you can see some of our customers and partners at the bottom. But I'd like to actually focus on the image on the left side of this slide, which is really this simple-looking, chart with stop train operation, de-ice plane, etc. This is a screenshot from our software tool that essentially translates this really complex data set that is weather into digestible, understandable insights for operators. And that can be a de-icing operation for an airline operating in Chicago O'Hare. It can be a railway dispatcher in the middle of the US, or it can be a farmer in Africa. All of these people have to make decisions for their day-to-day work, day-to-day operation that are sensitive to weather. They don't know how to read synoptic maps. I'll tell you a little secret. I was a pilot in the military. I would say, a pretty sophisticated weather user. I don't know how to read these maps either. So you need something that is much more simple and much more digestible to make it to the kind of what we call the last mile, or the actual individuals who are making decisions. So as a company, we focus on that, and that's kind of the flow of our work, starting actually from the right, which is the platform, the weather intelligence tool we have, serving, again, hundreds of customers all around the world today, from largest airlines in the world to over 6 million farmers in Africa today. Behind that software, we have a modeling team that actually focuses predominantly on AI-based models. We don't try to compete or replicate the efforts that our colleagues over at NOAA are doing. We're actually saying what is left to be done for the private sector, what are the things that are not addressed, and solve for these. And then last but not least is our proprietary sensing network from space, which I'll touch on. So this is, again, kind of a simple visualization of how we take left side complex weather events. We build protocols of if this, then that, if the wind exceeds this threshold and temperature is below this threshold. We incorporate it with probabilities because nothing, of course, is certain. So we can say, I want to be alerted if the probability for this is over 50%. And then at the end of the day, you're able to send simple messages via text, via email, via WhatsApp to all of your colleagues in your organization. Touching on our satellites, so connecting back to the map I showed in the first slide, this gap of observations, particularly for precipitation, for storms, is something we care deeply about from our users' perspective. And so we set on a mission to solve it, building a constellation combining both radiometers. So these are microwave sounders. For those who know what they are, they're essentially instruments who listen to the atmosphere and can see water temperature, humidity, and clouds. And that's what you're seeing at the bottom left, as well as weather radars, which we put in space. Today we have 4 satellites on orbit. We have over a dozen on the assembly line, so 2 more launching by the end of this year and another 10 or so next year. And what you're seeing on the right-hand side is some of the first scans we took with our microwave sounder. We're actually very proud to be working with our friends at NOAA, at NASA, sharing the data with them and hopefully getting them to use it in their operational models very soon. And this is one of really interesting results I want to show of what kind of data gaps we have and how proprietary observation and AI approaches can help solve them. So on the left side, you're seeing a product from MRMS, which is the multi-radar, multi-sensor precipitation layer that NOAA is producing. It's the best in the world, essentially the best algorithm for precipitation estimating globally. And you're seeing the coverage of the radar network of the US. This is the gray area. And you see a storm coming in. And essentially, when it is outside of that area, the coverage, there's nothing because there's no other sensors, and MRMS does not incorporate whatever little information we currently have from satellites. On the right-hand side, you see what AI can do to help with that, and AI and our satellite data. So this is an algorithm we call UP, which is Unified Precipitation, combining all the data that gets fed into MRMS with our satellites data and with new AI approaches of using existing other instruments. And you can see the full picture of the storm coming into the US from the Gulf of Mexico. Before I wrap, I just want to mention we also do a lot of work actually in Africa with smallholder farmers. So, you know, every company needs to look at becoming profitable and growing their revenues, and that's our large enterprise customers and government customers. But we also feel we have an obligation to support those at the kind of end of the pendulum who get the most extreme impact but may potentially not be able to pay just yet and use the solutions. So we have a nonprofit spin-out called tomorrownow.org, which is working with a great network of partners. I'll mention the Gates Foundation and USAID, supporting many programs of smallholder farmers in Africa. This is one of them in Kenya, where we support over 6 million farmers today with SMS messages telling them when to plant, when to seed, when to irrigate based on weather. So I think I'll wrap with that, and happy to take questions.
Okay, one just a quick initial question, and maybe I know you've addressed some of it already, but how are Tomorrow.io's weather products helping build resilience to climate risk and hazards in communities, particularly in developing countries?
Yeah, so I touched on it before, but I think, you know, maybe just to expand a little bit. So we talk a lot about weather, about climate. Sorry, you don't see a lot of weather words in this conference. Weather is climate, right, on a daily basis. So when we think about climate resiliency, we have a lot of activities to do in the long-term planning, but we first and foremost need to make sure that we're able to deal with the next storm, the next flood, the next, severe event. And to do that, we work with developing countries in many different models to enable our technology and our solutions to be used and adopted by those who need them most. So I want to emphasize that even though, we spent hundreds of millions of dollars to date developing technologies that are really built for what we call the global south, right? Like satellites that can replace ground radars, cloud computing that can replace on-premise, and so on, making those solutions much cheaper and much more easier to deploy. But it doesn't end there. You also need to think about what business model, what approaches can work so that these systems can be utilized in scale, because that's something that to date we've not really been able to do is in supporting all of these countries, and that's what we focus on a lot.
Thank you. We're going to we have time for some more questions in just a moment. In fact, as you're getting questions ready, I'll ask our panelists just a couple of sort of quick questions. So we've seen some really exciting developments with respect to the modeling efforts that are undergoing at NOAA, both for the entire Earth system. We're seeing some really exciting technologies that Tomorrow.io is spearheading with respect to the microwave sensors as well as spaceborne radar. I'm curious, what do you see as major gaps? This is a question addressed to both of you. Major gaps that still need to be addressed to make these technologies as useful as possible in ocean and climate spaces.
One of the primary things that are really needed are observations, not, and very specifically subsurface observations. I think I think the notion that oceans are just something that are influential over the long run, over the long time scale, is I think no longer correct, because they are actually influencing the sort of heat flux and the currents at even 2-kilometer depth are starting to influence seasonal predictions. And so subsurface observations is the biggest gap. The other, the one region I would sort of classify as being very important in terms of observations where the observation is scarce is the Southern Ocean, the high latitudes in Southern Ocean, because that region is very influential in both determining the physical aspects of the climate system, not just around the Antarctic and the Drake Passage, etc., but that actually influences the weather over the rest of the southern hemisphere, as well as propagating into the northern hemisphere through ocean connections. So I think that those two factors are very important in terms of the gaps we have. And without that, high-resolution modeling, AI, is not going to be able to cover all the gaps that the lack of observations are actually providing us now.
Yeah, so definitely agree on observations. I think the other piece I'll emphasize is what do the end users need, and thinking backwards and solving backwards from the operators, right? So we tend to think a lot about technology and science and start from there. So we develop new sensors based on science. We develop new modeling based on what the scientists think is needed or cool or interesting. We less so think of what's bothering a farmer in Nigeria right now. What's bothering communities in Latin America or even in the U.S. And then let's solve backwards. So so that's a problem for them. They don't get a long enough lead time for their next tropical cyclone. How do we solve backwards? What are the things we need solutions we need to implement in order to make their lead time longer? We need better observations. We need different types of models. Okay, let's work from there. So that I think approach would take us a much longer way.
Okay, we have some time from the audience. And while you're still thinking of questions, Ram has something else he'd like to add.
Yeah, I emphasize the observations because I think that is the most important gap. The next important thing is actually the modeling on the regional space scales, both in the oceans and the atmosphere. But going beyond that to actually do the explanation and interpretation of what comes out of the models and what it means, even in terms of like early alerts of some environmental hazard. It is something that really all sectors of society need, and as early as possible, that they'll say. But I think that's where the improvement in modeling through understanding of the physical processes, the dynamical processes, even chemical processes, but also how efficiently we can actually power these models through AI and do it in a way that actually makes the models even more reliable and robust. How can we do that would be kind of still an outstanding question.
Okay, thank you. Yes, sir.
Thank you. I'm Vladimir Rybinin. I used to work for the Intergovernmental Oceanographic Commission of UNESCO, and with Ram we worked for the World Climate Research Program. So maybe it's for you, Ram, mostly. So the computing power used to be kind of progressing exponentially. Now there is a little bit slowdown in that thing. Of course, artificial intelligence can basically fill the gap. But according to your understanding, it's really kind of your what you feel about this. So the current resolution of the models that you use and that this is coming in the near future, is it enough to run everything in explicit mode, or still maybe some nesting is required? So where we are in this field, what are the prospects? Thank you.
Ron?
Yeah, I mean, I think I'll take a shot at it and then you can continue. I think, we are getting into high resolution models, and the regional aspects are tying in very nicely to giving you more information on aspects of the system that you can't really resolve with global models. But I think enough. I think we need emulators, where these emulators through the AI can get to very high resolution. But then, we shouldn't fall into the trap of believing that high resolution necessarily will give you the most robust results. It may not. In fact, there are instances where high resolution actually degrades the model. It's because models are computer tools that are optimized. And the optimization designed for a certain class of problems may not work with other class of problems. So one has to be careful. But I think there still is the fact that we are, I think, at the low end of this pole to try emulators. So we can actually improve upon the emulations and work it towards a regime where we are getting fine-scale information, but also making sure that they're also reliable and trustworthy. That's as just getting to high resolution. So my answer would be emulators are going to help in this regard. The question was operating on tropical cyclones. Yeah, I mean, tropical cyclones, I think basically involve issues of, just as temperatures in the ocean, but also convection. And convection, does seem like high resolution does provide you at least the tool to get at those scales. Now the question is, are those tools enough to get you reliable results? And I think I would still pose that as a question. I don't think we have a definitive answer on that as yet.
Can't add much after that, but I think what we're seeing now with cloud computing is that the compute power is not really a limitation. It's infinite. It's more of like cost effectiveness versus other things that can move the needle on performance. So you could tune the model to run at 3 or even 1 kilometer global scale with the amount of nodes we have available today. Do we have the observations to actually make the model better is the question, right? Do we have the physics? And that's, I think, where we're going and where AI can actually help a lot.
And I would add just one other aspect of that. It's the observations, it's the modeling and the higher resolution, but it's also going to be how we connect those observations with the model itself. The data assimilation aspects of it as well, they're going to be critical. I see another question.
Yeah, thanks very much. Really interesting talk. My name is Claire Ayres from the Korea Polar Research Institute. I agree very much with your statement about the need for observations. And just wanted to ask particularly about the Southern Ocean, given the challenges of getting there, the difficulties of working in that region, and given so many polar programs are really being cut right now. Do you see a role for AI in trying to make better use of observations we have, or perhaps even deciding where we need to make those sorts of observations?
First, we fly in polar orbits, so we fly 100% duty cycle, so we get observations from the poles, not surface, of course, from space. But I think that what we're seeing also, and obviously you'd have much more to say about it, is that these models help us still to bridge the gaps better than we could before. So I think with more commercial observations from space, by the way, from the ocean as well, there are partner companies of ours who deploy buoys and others, and they can get to the poles. And AI, we should expect to see improvements there as well.
Yeah, this is a very important point, Southern Ocean. And there are two things that observations, it would be nice to have improved observations besides the polar observations that are there. And in terms of in situ observations, one is what's happening to the ice under the ocean. And trying to do that observation is, I imagine, I am not an observation person, but I imagine, I hear it's very difficult to do those autonomous glider observations under the ice. But that's very important because that's kind of where, if we are to understand the ice melt for example, under these big ice sheets, what is happening there is something that's still not well known, well observed, and models will have a tough time getting there. So it's really observations that have to be there. And the other place is the ice sheet itself. The dynamics of the ice sheets. We're just starting to get into that, from the satellite perspective. But what is happening, in terms of are there fissures in the ice? Are there sort of cracks in the ice sheets? We need some more observations to guide our models, because I think the land ice sheet, essentially as the warming is going on, what exactly is happening to that? How stable is it? And when can we say something about instabilities in that ice sheet? Are something that I think observations are needed to guide us into actually resolving what is going to happen to the ice sheets between now and 2100. 2100, maybe we know what will happen, but what's going to happen in the decades between now and 2100 is a question.
Right. Thank you for that question. I think another aspect of this is, given credible models, you can also do sensitivity analyses to identify where adding particular observations and of what type are going to have the most impact on improving your forecast of phenomena in a particular area. Because the reality is we don't have the resources to just flood the globe with observations of the surface ocean and the subsurface ocean, as Ram indicated. But we do have capabilities to allow us to identify where particular sensitive regions of where additional observations would help us improve the analysis and subsequent forecast over a given region. And so I think AI could certainly be a transformative tool in helping enhance that possibility. Thanks for your question.
Thank you very much. And I'm Hiroaki Shibuya. I'm a deputy director of the APN Secretariat. And so, yeah, so the AI is a very powerful tool. So the high resolution model was now, so they include nutrient, and so the productivity is also included. So how the model can support seafood resource management. So this is very important for the discussion with fishermen and policy makers to maintain the seafood. So I think the AI is very powerful too, and so that it will be visualize the seafood. So yeah.
Okay, thanks for that question. And the question's about how AI can be used to help enhance our understanding of fisheries and fishery management. And I would say that, as Ram had indicated, and I'll turn it over to him in just a moment, there is within NOAA the Climate Ecosystems and Fisheries Initiative, which has started out with a more maybe traditional physics-based model approach, but coupling in ecosystems. So we have a whole Earth system model coupled with ecosystems to allow us to understand the evolution of fisheries and the climate, the environment, the ecosystems with which various fish species reside. And so by improving forecasts of that, we can then understand how those ecosystems are changing over time and help predict the evolution of fisheries. But AI could certainly help power that, enhance that more by perhaps having emulators of some aspects of the ecosystems as well as the physical processes. But I'll turn it over to Ram for...
Yeah, that's right. I think I'll just continue on that point. The use of AI and emulators in terms of simulating all those physical, chemical, biological, dynamical occurrences along the coastline is assuming very big proportions in terms of the whole area of modeling with AI tools. One of the things that is happening in NOAA right now is this is being put to test for seasonal predictions of things like nutrients, like chlorophyll, I forget everything, but a lot of nutrients which are in the biogeochemistry models, plus the prediction of ocean currents along the coastlines. And this in turn feeds into fish population models. So, it's like a marriage of physical models and fish population models. And the first test is really how do the seasonal predictions, how are they utilizable by the fishing community, by fisheries management? And so this is an important test. I think it's still early to say, what the success is. or what the rate of success is, but it is a very promising venture where you are really bringing two communities together, which kind of was not possible, even 10, 15 years ago. But it's happening now, and so I think it's going to grow. I mean, initially there might be some not so great successes, but it is something that is now happening and is there to stay. So I think it's a very promising venture that we are embarking on.
Okay, one last question.
Can you hear me? Okay.
Yes.
Thank you, everyone, for the informations. As someone who's passionate emerging tech and AI, as a computer science student, I would like to ask you, where do you see the future of AI and all the technologies going in the next 5 years or 10 years? As we've seen, the technologies are now already helping so much. How do you see all the techs that we have is going to help in another vision in the next 5 years? Or how developed are they going to be? Do you have an idea about what will the future hold?
Well, I would say that even trying to predict 6 months to a year in advance about what emerging technologies are going to be there, I think is a grand challenge in and of itself. And so looking a decade ahead is going to be certainly problematic. You're going to probably miss the mark by a large amount. But I would say within NOAA, we're going to be accelerating our use of AI in a number of different areas, in our fisheries management, in our modeling efforts, in our data assimilation, data acquisition and processing of our data, as well as looking at, I mentioned before, these subsurface microphones, sonographs that we can allow for something like a Shazam for whales. We can actually understand where whale species exist by having recordings of them, those being trained on this species identification, so that when we hear a particular sound emitted from a marine mammal, we can detect this is what it is, this is where it is. I think is going to be something that's incredible. But we're going to see just an expansion of this within the context of our environmental prediction and providing environmental intelligence to the world. AI is going to be fully embedded in that, I imagine. But I'm going to turn it over for the last couple of remarks from our panelists, because they may have a different perspective.
Yeah, I agree. 10 years out is quite a quite a range. We're probably all going to be replaced by machines. But one thing I will say is where we've seen people being really effective in using AI is when they also understand the context, right? So you see a lot of people with zero atmospheric science or physics or whatever background trying to get into weather, and those who actually have the physical background as well do much more and are much more effective using these AI tools to help advancing the science and the technology. So I would say whatever you choose to do, also make sure you understand the context and not just the computer science aspects of it.
Nothing more to add.
Yeah, that was an excellent response. Thanks, Ray, on that. And also, it's not just the adoption of AI, but it's also the adoption truly of trustworthy, reliable AI. So it has to go through a really rigorous process of validation, getting back to the understanding aspect of it, but also making sure it's fit for the purpose that's intended. Thank you.
If I may just add, there are too many AI sessions we've been in, and the bottom line that was given to us, you have to use human intelligence to decide where to use AI and how. So I guess that's a big theme driving all of us. Thank you for the excellent panel. Cheers.
Oh, thank you very much. And again, I'd like to thank the Ocean Pavilion for hosting this particular session, and I'd like to thank you all for your wonderful questions. And let's thank our panelists, please. They did a wonderful job. Have a great afternoon. Thank you.